Welcome, friends. So, last lecture we have discussed the idea of resistance. Now, in this lecture, or in this part of this lecture, we shall discuss the next element, that is called inductance. Now, to understand the concept of inductance, let us consider this figure 3, where we have a conductor of, let us say, iron, and a wear is wound on the conductor like this, okay, it is like this. Now, if the conductor or wire is connected across the supply, a current starts flowing. Now, if the current will be starts flowing in this direction, that means it is in the clockwise direction. Current may be flowing in anti-clockwise as well. So, depending on the flowing of the current, a magnetic field will be setting up, and these red lines, will be directed and is the direction of the magnetic field. Okay, so these lines are the direction of the magnetic fields. These lines. So it is directed along this. So this will form a shape like this. Okay, the lines of magnetic lines of forces. So this will be forming something like this, magnetic lines of forces. So the magnetic field lines will be like this. Now the reason, now the question comes that why this direction? Why not this direction? Why not this direction? The answer to this, let us consider my right hand. Now this 4 fingers, if you bend it like this, so I am bending it like in anti-clockwise direction, right? Now, if the current flows in the anti-clockwise direction, then your magnetic field should be directed along such a distance which is directed by this thumb. So, if the current flowing in the anti-clockwise direction, see, this direction is anti-clockwise direction. This direction is anti-clockwise direction, this bending, okay. So if my current is flowing in the anti-clockwise direction, then the direction of my magnetic field will be directed along the direction which is directed by the this thumb. On the other hand, if the current is clockwise direction, now this is my clockwise direction, these 4 fingers. So if the current is flowing in the clockwise direction, then the direction of the magnetic field will be such a direction which is directed by this thumb. So it will be in this direction. So it is called right hand thumb rule. So let us say if this current is flowing in this direction, if the current is flowing it is clockwise direction, right? It is, you see, current is flowing in clockwise direction. Current is flowing in, this is the clockwise direction. Through the conductor, current is flowing in the clockwise direction. So as per the thumb rule, as per the right hand thumb rule, so if this is the clockwise direction of rotation, so magnetic field will be directed, you see, it is the directed along this direction, directed along the bottom surface. So that is the exactly the direction of the magnetic field in this way. So you can say that this is effectively north pole of the electromagnet, and this becomes the south pole. Now if you change your current direction, then direction becomes anti-clockwise, then the magnetic field direction will be in this way. So it is determined by a rule which is called right hand thumb rule. Now suppose a current is flowing I, and accordingly a magnetic field is set up as shown in this figure. So there is a definite relation between this current flowing and the magnetic field. So due to this magnetic field, whatever magnetic field is set up, it is linking with these turns, linking with this conductor, which is defined by N phi, which is called flux linkage, which is defined by flux linkage. That means amount of flux, magnetic flux linking with that conductor or linking with the coil. So this flux linkage is directly proportional to the current. Why? Because the current, if amount of current is more, then flux linkage will be more. That is the directly proportional relation. So if you bring a proportionality constant, it becomes N phi, it will be equal to L into I. So inductance basically, which is inductance basically defined by flux linkage per current, flux linkage per current. The unit should be, flux linkage is Weber turn and current should be ampere, and most sophisticated way of representing inductance is, or most practical way of representing inductance is in Henry. So what is the definition of inductance? Inductance is a parameter due to the electromagnetism, and this is defined by flux linkage per unit current. It is defined by flux linkage per unit current. This is the definition of inductance. Unit is Henry. Now it is well known relation that flux linkage of a solenoid is given by this formula, L is equal to mu naught N square A by L, where mu naught is equal to 4 pi into 10 to the power minus 7 Henry per meter. It is called absolute permeability. N is the number of turns. What is A? A and L is the same. It is the cross sectional area, and L is the length of the conductor. It is the same. So we can understand one thing, that if the current is flowing, a magnetic field will be set up. So if a magnetic field will be setting up, then a magnetic flux will be created. If the magnetic flux is created, then flux linking will be there, flux linkage will be there. So it comes that the flux linkage will be more if the current becomes more. If the flux linkage becomes less if the current flows less. So there is a direct relation. Flux linkage is directly proportional to the current flowing through the conductor. And its direction of the magnetic field is governed by this rule, right hand thumb rule. Now Let us consider another case, that is concept of mutual inductance. What is mutual inductance? Now let us consider figure 4 where you have two conductors or you have two electromagnets, right? This is electromagnet 1, this is electromagnet 2. Now in this case one current is flowing I1 and in this case one current is flowing I2. So due to the flowing of I1, you see this direction is this direction, so it is clockwise direction, the current, so magnetic field will be in this direction. However, for the second electromagnet, the direction is just changed. It is okay, it is in this direction, anti-clockwise direction for the second electromagnet. So the magnetic field is in this direction. So now if we were now try to draw one such pattern of magnetic field lines, let us try at least one. So you see this line maybe looks like this and maybe this line maybe looks like this. So what is important here is that the sum part of the magnetic flux of solenoid 1 or electromagnet 1 will be linking to the solenoid 2 and vice versa. Some part of the magnetic field of conductor 2 or solenoid 2 will be linking to the flux linkage of or coil of the conductor 1. So that is there is a definitely, it is well understood that there is a mutual coupling or mutual we have a mutual coupling effect or mutual linkage effect. What do I mean by that? So let us say current I1 is generating flux phi 1 at the solenoid 1 or electromagnet 1. I1 is generating phi 1, and similarly for electromagnet or solenoid I2 it is generating phi 2. Now the problem here is that, not problem, it is the some part of the I1 or some part of this phi 1 will be linking to this solenoid 2 and some part of this phi 2 will be linking solenoid 1. So here comes the mutual coupling or mutual linkage effect. So what we can write here is that to understand this effect we can write the flux linkage of solenoid 1 N1 phi 1, that is L1 I1, we know this term till now, but there is a mutual effect. There is a, due to the current flowing to in the solenoid 2, that is I2, there is a also a effect due to the current flowing to I2. So that is called the mutual inductance. That is called mutual inductance. So L here is called self inductance and M here is called mutual inductance. Both are having unit Henry. So we have similarly for flux linkage at solenoid 2 N2 phi 2 is given by sorry, this relation L2 I2 plus M into I1. So equation 6a and 6b represents the effect of mutual coupling or mutual linkage. Effect of mutual coupling or linking. Also now we have some diagrams. Let us say two conductors are connected in series. Now how equivalent inductance are formed? Let us say now these black dots, nothing but they are the polarity of the potential at any instant. Now if this polarity is shown as shown in figure 5a, they are called additive polarity. They are called additive polarity. Figure 5a and figure 5b. They are called additive polarity. Why? Because with respect to each polarity, the current is leaving. And for 5B, with respect to each polarity, current is entering to the dot. So it is called dot convention. So in case of a additive polarity, the equivalent inductance becomes this: L1 plus L2 plus 2M. L1 plus L2 plus 2M. So if you neglect mutual effect, then it is only become L1 plus L2. It is become L1 plus L2 with no mutual effect, with no mutual effect. However, if you consider 2M, or if you consider the mutual effect, then this 2M terms comes. Now if you consider figure 5C and 5D, so this type of polarities are called subtractive polarity, because with respect to the first dot, current is leaving, but with respect to second dot, current is entering. So it is represented by L1 minus M and L2 minus M. So equivalent inductance is L1 plus L2 minus 2M. Now with respect to figure 5D, again it is a subtracted polarity, because with respect to the first dot, current is entering, but with respect to the second dot, current is leaving. Same current is flowing, but one is entering to the dot, for second dot it is leaving. So each inductance is represented by L1 minus M and L2 minus M, because M is opposing each other. So equivalent inductance is L1 plus L2 minus 2M. So for additive polarity, we have L equivalent is equal to L1 plus L2 plus 2M. For subtractive polarity, we have L1 plus L2 minus 2M. Now we can also have a parallel circuit. So this is the additive polarity, figure 5E. This is the additive polarity. So for additive polarity, this is the equivalent inductance. And for subtractive polarity, figure 5F, so this should be the equivalent inductance. So if you consider closely, for series connection of inductance, if you don't consider the mutual effect, it is only L1 plus L2, as we have found in case of a resistor. Similarly, if you consider M is equal to 0, that means no mutual coupling, so you will find that is equivalent inductance is simply by this formula L1 L2 divided by L1 plus L2. That we have exactly this result we have seen in case of a resistance. So resistance and inductance equivalent calculation is similar. Now let us consider a comparison between electrical circuit and a magnetic circuit. Let us consider. Now electrical circuit is represented by this diagram, figure 6a, where a resistance is there, a source is there, and the current flowing is there. And it is given by this relation, V is equal to R into I. Voltage is equal to resistance into current. That is Ohm's law. So we have got from resistance, from the Ohm's law, we have got for electrical circuit, voltage is equal to current into resistance. However, in case of a magnetic circuit, as shown in figure 6b, we have a solenoid, one current is flowing, and we have a turn. So we have a relation something to Ohm's law, equivalent to Ohm's law, which is called MMF is equal to flux into reluctance. MMF, that is equal to flux into reluctance. So who is the driving force in case of an electrical circuit? It is the electromotive force EMF, or simply voltage. This is the driving force. Now in case of a magnetic circuit, it becomes the magnetomotive force MMF. The unit is ampere turn. Unit is ampere turn. Now which is flowing, or what is flowing in case of electrical circuit? The answer is current. Current is flowing. Now in case of a magnetic circuit, it is flux is flowing. Now the material through which the conductor flow, or the material through which the current flows, it is called resistance. That is the opposing parameter. And in case of a magnetic circuit, it is called reluctance. Its unit ampere turn per Weber. Now moving to the next point, what is the medium? That is the medium through which the current is flowing. It is characterized by a parameter, it's called conductivity. However, in case of a magnetic circuit, the medium, it is characterized by a permeability, which is called mu. Now the resistance is given by this formula, R is equal to rho L by A, and reluctance is given by this formula, S is equal to 1 by mu naught L by A. And we have the Ohm's law, voltage is equal to current into resistance, and MMF is equal to flux into reluctance in case of a magnetic circuit. So this is a brief comparison between electric and magnetic circuit. Now in case of now quickly recap what we have gone through quickly. Now first of all, inductance is the ratio between flux linkage to the current. Unit is Henry. A potential drop of an inductor is L di dt. We shall see this expression later on this course. Now power dissipated, that means active power, one is P and another one is reactive power P. Now in case of active power, it is 0 for inductor. Now for a reactive power, an inductor always absorbs reactive power, which is called lagging var. That means if an inductor is there, it always absorbs, that means it always takes reactive power. That is, this is called lagging var. Now energy stored in the inductor, it is given by half Li square. It is the 10-12 standard physics, you should know that. Inductance of a solenoid is given by this formula, mu naught n square A by L. Now reluctance is given by this formula, 1 by mu naught L by A, very important relation. Equivalent inductance in series, it is L1 plus L2. Now with mutual effect, as I said, it should be plus minus 2m. For additive polarity, it is plus 2m, and subtractive polarity, it is minus 2m. Now equivalent inductance in parallel, it is L1 L2 by L1 plus L2. Now in case of inductance in parallel, we have an extra term, which is in the numerator we have minus m square, and in the denominator we have 2m. Now it is last thing I like to mention here is that now inductance is formed due to the flux linkage. Inductance is formed due to this flux linkage. One current is flowing through the coil, and that this magnetic field, how much magnetic field is linking with this coil. So So due to this linking effect, the idea of giving the symbol of the inductance is chosen in this way. So it is like a linking mechanism, right? It is like a linking. That is why the inductance symbol is given in this fashion. So we have discussed various aspects, very brief idea about the inductance. So I am stopping here. So in the next part of this module will be discussed in next few lectures. Thank you.